Hey there, night owls. Welcome back to Late Night Science. It's late. The world's quiet. Maybe you're lying in bed scrolling through your phone, or sitting at your desk unable to sleep, wondering about the big questions. You're in the right place. Tonight, we're diving into something that's been keeping some of the world's brightest cosmologists awake at night. And I'm not exaggerating when I say this might be one of the biggest scientific stories of our lifetime. The James Webb Space Telescope, humanity's most powerful window into the cosmos, a 10 billion marvel of engineering, was launched with a clear mission. It was supposed to look deeper into space and further back in time than ever before. It was supposed to show us the baby pictures of the universe. The first stars igniting, the first galaxies forming, the cosmic dawn. Most importantly, it was supposed to confirm what we thought we knew. To validate a century of physics. To put the final, beautiful stamp on the Big Bang Theory. Instead, James Webb might be tearing apart the most fundamental story we've ever told ourselves about existence. I'm talking about galaxies that shouldn't exist. Stars forming impossibly fast. Black holes appearing billions of years before they had any right to. Structures so massive, so organized, so perfect that they break every timeline we've constructed about how the universe evolved. It's like opening a time capsule from what you thought was ancient history, only to find a smartphone inside. So grab your coffee or tea, get comfortable, and let's explore what might be the beginning of a revolution in cosmology. Because what James Webb is showing us isn't just surprising, it's fundamentally challenging whether we understand the universe at all. CTO1THESCOP and THTHEOY. What James Webb actually is. Before we get into the bombshells, let's talk about what the James Webb Space Telescope actually is. Because this isn't just a bigger, better Hubble. James Webb is fundamentally different. It took over 3 decades to develop, involved thousands of scientists and engineers from 14 countries, and cost nearly $10 billion. When it launched on Christmas Day 2021, it represented the most ambitious space observatory ever attempted. The telescope sits nearly a million miles from Earth, at what's called the second Lagrange point, or L2. This is a special spot in space, where the gravitational forces of the Earth and Sun balance out, allowing the telescope to orbit the Sun alongside Earth while using minimal fuel to stay in position. Why so far away? Because James Webb needs to be cold. Really cold. Its instruments operate at temperatures close to absolute zero, about -400 degrees Fahrenheit. At these temperatures, Webb can detect the faintest heat signatures from the most distant objects in the universe. To achieve this, Webb is protected by a massive sun shield the size of a tennis court. This 5-layer shield keeps the hot side facing the sun at about 200 degrees Fahrenheit while the cold side, where the instruments live, stays frigid. The temperature difference between the two sides is comparable to the difference between boiling and freezing water, but far more extreme. The telescope's primary mirror is 21 feet across, about 2.5 times the diameter of Hubble's mirror, and it's made of 18 hexagonal segments coated in gold. Why gold? Because gold is highly reflective to infrared light, which is exactly what Webb was designed to see. And that's the critical difference. Hubble looks primarily at visible and ultraviolet light, the kind of light our eyes can see. James Webb looks at infrared, heat radiation that's invisible to us. Why does this matter? Because of something called redshift. Understanding redshift, the key to cosmic time. When you hear an ambulance approaching, its siren sounds higher pitched. As it passes and moves away, the pitch drops lower. That's the Doppler effect. Waves get compressed when the source moves toward you and stretched when it moves away. Light works the same way. When an object in space moves away from us, its light waves get stretched. Blue light, which has short wavelengths, gets stretched into red light, which has longer wavelengths. We call this redshift. But here's where it gets interesting. The universe is expanding. Space itself is stretching, carrying galaxies away from each other. The farther away a galaxy is, the more space has expanded between us and it, and the more its light has been redshifted. This means redshift isn't just about motion, it's about distance and time. A galaxy with high redshift is not only far away but also far back in time. Because its light has been traveling to us for billions of years, while the universe expanded around it. The most distant galaxies have been traveling so long that their light has shifted from visible wavelengths all the way into the infrared. That's why we needed James Webb. Hubble couldn't see them clearly, because they'd redshifted beyond visible light. When we talk about a galaxy at redshift 10, we're seeing it as it existed when the universe was only about 500 million years old, less than 4% of its current age. At redshift 16, we're looking back to just 240 million years after the Big Bang. This relationship between redshift, distance, and cosmic age is the foundation of observational cosmology. It's how we measure the universe's history. And as we'll see, it's one of the things James Webb is now calling into question. The Big Bang Theory, what we thought we knew. Before we can understand what's being challenged, we need to understand what the Big Bang Theory actually claims. And no, it's not what most people think. The Big Bang wasn't an explosion in space, it was space itself beginning to expand. Imagine the universe not as objects flying apart through an empty void, but as the fabric of reality itself stretching, carrying everything with it. The theory proposes that roughly 13.8 billion years ago, all of space, time, matter, and energy were compressed into an extraordinarily hot, dense state. Not a point in space, because space didn't exist yet as we know it, but rather space itself in a collapsed form. Then expansion began. In the first fraction of a second, a period called cosmic inflation, the universe expanded exponentially, faster than the speed of light. This sounds like it violates physics, but it doesn't. Nothing was moving through space faster than light, space itself was expanding, and that's allowed. After inflation, the universe continued expanding but at a slower rate. It was incredibly hot, trillions of degrees. For the first few minutes, conditions were so extreme that protons and neutrons could fuse into the lightest atomic new hydrogen, helium, and tiny amounts of lithium. This is called Big Bang nucleosynthesis, and it explains why the universe is about 75% hydrogen and 25% helium by mass. For the next several 100,000 years, the universe was a hot, opaque plasma. Electrons and nuclei zipped around freely, and light couldn't travel far before being scattered. The universe was literally glowing, but you couldn't see through it. Then, about 380,000 years after the Big Bang, something important happened. The universe had cooled enough for electrons and nuclei to combine into neutral atoms. This moment is called recombination. Suddenly, light could travel freely. The universe became transparent. That light, the first light to travel unobstructed through space, is still reaching us today. We call it the cosmic microwave background, or CMB. It's like the universe's baby picture, showing us what things look like just 380,000 years after the beginning. After recombination came what astronomers call the cosmic dark ages. The universe was full of neutral hydrogen gas, but there were no stars yet. No light sources, just darkness and gas slowly being pulled together by gravity. According to our models, it should have taken hundreds of millions of years for that gas to collapse into the first stars, massive hot, metal-free stars called population-Athu stars. These first stars would live fast, violent lives, exploding as supernovae and the first heavy elements into space. From there, successive generations of stars would form, increasingly enriched with heavier elements. These stars would cluster into the first galaxies, small, irregular, chaotic things, nothing like the grand spirals we see today. Over billions of years, these proto-galaxies would merge and grow. Larger structures would form galaxy clusters, superclusters, the cosmic web of filaments and voids that makes up the large-scale structure of the universe. This timeline, slow, gradual, building from simple to complex, is the heart of the Big Bang model. Simple ingredients at the start. Time for gravity to do its work. Structure emerging incrementally over cosmic history. Everything we've observed for decades supported this picture. The cosmic microwave background showed the tiny temperature fluctuations that would grow into galaxies. The abundance of light elements matched predictions. The expansion of space was directly measured. Galaxy surveys showed how structure evolved over time. The Big Bang wasn't just speculation, it was a tested, validated framework with enormous predictive power. The evidence that built confidence. Let me walk you through the pillars that made the Big Bang theory so dominant. Elf and cosmic expansion. In 1929, Edwin Hubble made one of the most important discoveries in astronomy. By measuring the light from distant galaxies, he found that nearly all of them were redshifted, moving away from us. More importantly, the farther away they were, the faster they were receding. This wasn't random motion. It was systematic expansion. And if everything is moving apart now, that means it was all closer together in the past. Rewind far enough, and you reach a beginning. Pillar tuning the cosmic microwave background. In 1964, Two radio astronomers named Arno Penzias and Robert Wilson were testing a new antenna when they detected a persistent noise coming from every direction in the sky. At first, they thought it was interference, maybe pigeon droppings in their antenna. But it wasn't. It was the cosmic microwave background, the cooled-down remnant of the hot early universe. This discovery was such powerful confirmation of the Big Bang that Penzias and Wilson won the Nobel Prize, later Satellites in 1989, WIP in 2001, and Planck in 2009, mapped the CMB in exquisite detail. They found tiny temperature variations about 1 part in 100,000, representing the quantum fluctuations from the earliest moments that would eventually grow into galaxies. Pillar 3 light element abundances. When astronomers measure the composition of the oldest stars and gas clouds, they find a very specific radii-70, 25% helium, and trace amounts of lithium. This ratio matches exactly what you'd predict if these elements were forged in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion. No other theory predicted this. The Big Bang did. Pillar forcing large-scale structure. As telescopes improve, astronomers mapped millions of galaxies across vast regions of space. They found that galaxies aren't randomly distributed. They form a cosmic web, long filaments and sheets separated by vast voids. Computer simulations based on Big Bang cosmology predicted this structure. When cosmologists ran simulations starting from the tiny fluctuation seen in the CMB, and let gravity do its work over 13.8 billion years, they got something that looked remarkably like the real universe. These 4 pillars, expansion, the CMB, element abundances, and large-scale structure, made the Big Bang virtually unchallengeable. It wasn't just a good idea. It was an extremely well-tested scientific theory that had passed every major test thrown at it. Scientists were confident enough that James Webb was designed not to test whether the Big Bang happened, but to fill in the details. To see the first stars, to watch the first galaxies forming, to refine our understanding of those early epochs. Nobody expected James Webb to challenge the foundations. Webb's first images, beauty and confusion. When James Webb's first deep field image was released on July 12, 2022, the world gasped. The image showed thousands of galaxies in unprecedented detail. Graceful spirals, massive ellipticals, distant red smudges representing some of the most ancient galaxies ever taken. It was breathtaking, a cosmic masterpiece painted in gold and crimson. But astronomers looking at that image saw something else: problems. The galaxies Webb was finding at high redshifts, the most distant, most ancient ones, didn't look like babies. They didn't look like the chaotic, irregular, small proto-galaxies that should exist in the early universe. They looked mature, organized, massive. In the following weeks and months, as more data came in, the problem became clear. Webb was detecting galaxies at redshifts of 10-12, even higher, galaxies existing just a few hundred million years after the Big Bang. According to the Standard Model, these should be the cosmic equivalent of newborns. Simple structures just beginning to form. Instead, they had masses comparable to our Milky Way, a galaxy that took over 13 billion years to assemble. They showed organized rotation. Some had distinct structural components like disks and bulges. Their stars contained significant amounts of heavy elements, implying multiple generations of stellar evolution had already occurred. One astrophysicist described it bluntly: these galaxies shouldn't exist. Another compared it to walking into a nursery expecting to see infants and finding a room full of 30-year-olds. It wasn't just 1 or 2 anomalies. It was a pattern, a population. Too many galaxies, too massive, too soon, too organized. The timeline was broken. The crisis begins to unfold as spectroscopic confirmations came in. Detailed analysis of the light from these galaxies. The initial shock hardened into a genuine puzzle. Galaxy CRS-93315, observed at a redshift around 16.7, appeared to exist just 240 million years after the Big Bang. Models suggested the universe barely had time to form any stars by that point, let alone organize them into galaxies. GNZ11 confirmed at redshift 10.6 showed a stellar mass of about 1 billion times the mass of our Sun. It existed just 14 million years after the Big Bang. Galaxies Z13 and Galaxies Z11, both spotted in early Webb data, pushed the boundaries even further. And it wasn't just their existence, it was their properties. These galaxies were forming stars at rates that rivaled or exceeded modern star-forming galaxies. They showed signs of chemical enrichment, with significant amounts of oxygen, carbon, and other elements that should have required multiple generations of stars to produce. Some showed ordered kinematics, meaning their stars were rotating in organized patterns, not the chaotic motions expected from galaxies still assembling. Researchers started running the numbers. To form these galaxies in the available time, you'd need star formation efficiencies approaching 100%, meaning essentially all the available gas would have to turn into stars, with perfect efficiency and no waste. That's not how star formation works. Real star formation is messy, inefficient, with lots of gas blown away by stellar winds and supernova explosions. Typical efficiencies are more like 1%, not 100%. Even if you cranked up the efficiency to impossible levels, you'd still struggle to explain how these galaxies got so massive so quickly. And then there were the black holes. Webb detected active galactic nuclei, the bright signatures of supermassive black holes actively feeding in galaxies existing less than 700 million years after the Big Bang. Some of these black holes had masses of hundreds of millions of solar masses. Building black holes that massive should take billions of years, not hundreds of millions. Something was deeply wrong. Either our understanding of how galaxies and stars form was fundamentally flawed, or our timeline was off, or both. And if the timeline was wrong, that meant our most basic tool, using redshift to measure distance and age, might not work the way we thought. The standard model under strain, the standard cosmological model, formerly called TCDM, has been the backbone of modern cosmology for decades. It incorporates the Big Bang, cosmic inflation, dark matter, and dark energy into one comprehensive framework. James Webb's discoveries aren't just tweaking details. They're putting stress on the model's fundamental assumptions. Assumption 1: teen structure forms hierarchically over time. The model predicts small structures form first, then merge into larger ones over billions of years. But Webb is finding large, organized structures appearing almost immediately. Assumption 2 says star formation follows known physics. We understand how stars form, gas collapses, fusion ignites, feedback regulates the process. But the early star formation rates Webb is seeing push or exceed the theoretical limits. Assumption 3 chemical enrichment requires time. Heavy elements only form in stars and supernova explosions. Multiple generations are needed to build up significant metallicity. But Webb is finding metal-rich stars existing when the universe was supposedly too young for even one complete stellar generation. Assumption 14. Redshift reliably measures cosmic time. Our entire timeline is built on the assumption that redshift directly correlates with distance and age through the expansion of space. If this breaks down, everything else falls apart. The scientific community is beginning to grapple with an uncomfortable reality. Either something fundamental about our models is wrong, or we're misinterpreting the data in some systematic way we haven't figured out yet. Some researchers are trying to save the standard model by proposing modifications. Maybe dark matter behaves differently in the early universe. Maybe there are additional energy injection mechanisms we don't understand. Maybe star formation was just radically more efficient in the first billion years. Others are starting to look at alternative frameworks entirely. Models that have been sitting on the fringes of cosmology for decades, dismissed but never quite disproven. And a few are asking the most radical question of all: what if the Big Bang didn't happen the way we think? Or at all? We'll explore all of these possibilities, but first, we need to understand just how deep the rabbit hole goes. Because galaxies are just the beginning. The problems extend to stars, black holes, the cosmic web, and even the nature of space and time itself. Stars that break the rules. Let's talk about stars specifically, the first stars that should have existed in the universe. In the Big Bang model, the very first generation of stars, astronomers call them population E3 stars, should have been fundamentally different from stars today. They would have formed from primordial gas that was pure hydrogen and helium, with no heavier elements whatsoever. Why? Because heavier elements don't exist naturally. They're only created inside stars through nuclear fusion, then scattered into space when those stars explode. The first stars had to form from whatever the Big Bang created, which was just the lightest elements. These population E30 stars should have been massive, perhaps 100 to 1 times the mass of our Sun, burning incredibly hot and bright, living fast and dying young in spectacular supernova explosions. Their deaths would seed space with the first carbon, oxygen, nitrogen, iron, all the elements that make up planets and eventually us. Then second-generation stars could form from that enriched material. And third-generation stars would be even more metal-rich. Our Sun is probably a third or fourth generation star, formed from material recycled through previous stellar generations. This means metallicity, the presence of elements heavier than helium, is essentially a clock. High metallicity means many stellar generations have passed. Low metallicity means you're looking at early generation stars. Zero metallicity would be population of the first stars. Despite decades of searching, astronomers have never found a population of 3 star. Not one. Every star we've ever observed, no matter how distant or how old, contains at least some heavy elements. That was already puzzling. But James Webb has made it worse. Webb is detecting significant metallicity in galaxies at extremely high redshifts. Galaxies that existed just a few hundred million years after the Big Bang. We're talking about seeing spectral lines of oxygen, carbon, nitrogen, and even iron in stars that should barely have had time to form at all, let alone die and recycle their materials. In one study, researchers found galaxies at redshift 1013 with oxygen abundances comparable to much younger galaxies. Oxygen is produced in massive stars and dispersed by supernova explosions. To have this much oxygen so early means multiple generations of massive stars must have already lived and died. But there simply isn't enough time in the standard model. Let's do the math. At redshift 12, the universe was about 370 million years old. For metallicity to build up, you need gas clouds to collapse and form the first stars, those stars to live out their lives, supernova explosions to scatter the heavy elements, new gas clouds to form from the enriched material, second-generation stars to form and potentially repeat the cycle. Even in the most optimistic scenario, this process should take at least 100–200 million years per generation. If you're seeing significant metallicity at 370 million years, you have barely enough time for one complete cycle, maybe 2 if you're really pushing it. But the metallicity levels Webb is detecting suggest 3 or more generations. The math doesn't add up. Some scientists have proposed that star formation might have been hyper-efficient in the early universe, that stars formed faster, lived shorter lives, and recycled their material more rapidly than they do today. But this creates its own problems. Rapid star formation generates intense radiation and stellar winds that should actually blow gas out of galaxies, inhibiting further star formation. It's a self-limiting process. You can't just dial up the efficiency to 11 without causing other effects. There's also the question of what these early stars look like. Some of the stars Webb has detected are not only metal-rich but also extremely massive, possibly hundreds of times more massive than our Sun. Stars this large are theoretically unstable. Radiation pressure should tear them apart, or cause them to collapse into black holes. Yet here they are, shining brightly in the early universe, defying our understanding of stellar physics. The black hole conundrum: if early stars are problematic, early black holes are even worse. Supermassive black holes, the kind with millions or billions of times the mass of our Sun, are supposed to take a very long time to form. The traditional picture goes something like this: a massive star, perhaps 20–50 times the mass of the Sun, exhausts its nuclear fuel and collapses into a stellar mass black hole of 10⁻⁰ solar masses. This black hole sits at the center of a galaxy, gradually pulling in surrounding gas and dust through a process called accretion. There's a limit to how fast a black hole can grow. As matter falls in, it heats up and emits radiation. This radiation pushes outward, counteracting the inward pull of gravity. The balance between these two forces sets a maximum growth rate called the Eddington limit. Even at this maximum rate, growing a stellar mass black hole into a supermassive one takes time, typically hundreds of millions to billions of years. Additionally, supermassive black holes grow by merging. When galaxies collide, their central black holes eventually spiral together and merge into a larger black hole. Over cosmic time, through many mergers and steady accretion, you can build the supermassive black holes we see in the centers of most large galaxies today. Our own Milky Way has one Sagittarius A, with a mass of about 4 million times the Sun. It formed gradually over more than 13 billion years, but James Webb is finding supermassive black holes in galaxies that existed less than 700 million years after the Big Bang. And they're not small. CERS 119, a galaxy observed by Webb, contains a supermassive black hole with a mass of several million solar masses. It existed when the universe was about 570 million years old. Another system showed a black hole of hundreds of millions of solar masses, at even higher redshift. Even if you start with the largest possible seed, say a 100 solar mass stellar black hole, formed from a population phase star, and feed it matter at the maximum eton rate for the entire 570 million years available, you still can't grow it large enough to match what Webb is seeing. The numbers don't work. Some theorists have proposed alternative formation mechanisms. One idea is direct collapse. Instead of forming from a star, a massive gas cloud collapses directly into a black hole, creating a much larger seed to start with, perhaps 10,000 to 100,000 solar masses. This would give the black hole a head start. But even direct collapse black holes need time to grow to the masses Webb is detecting, and the timeline is still tight. And it's not just one or two cases. Supermassive black holes appear to be common in early galaxies. Webb has detected dozens of active galactic nuclei at high redshifts, the bright signatures of black holes actively feeding on surrounding matter. This raises a provocative question: did supermassive black holes form first, with galaxies forming around them? That would completely flip our understanding of galaxy formation. Instead of galaxies forming and then growing central black holes over time, maybe the black holes came first, and their gravity acted as seeds around which galaxies assembled. This isn't as crazy as it sounds. We know that supermassive black holes significantly influence their host galaxies. They inject energy into surrounding gas, regulate star formation, and shape galactic evolution. Maybe this relationship goes all the way back to the beginning. But if supermassive black holes existed before galaxies, where did they come from? Some cosmologists are now considering primordial black holes. Black holes form not from stars, but directly from density fluctuations in the extremely early universe. Perhaps in the first second after the Big Bang. If primordial black holes exist, and some of them were massive enough, they could serve as seeds for supermassive black holes and for galaxy formation itself. This is highly speculative. But the fact that serious scientists are discussing it shows how desperate the situation has become. James Webb isn't giving us easy answers. It's forcing us to reconsider assumptions we thought were settled. The cosmic web: too much structure, too soon. Let's zoom out from individual galaxies and look at the large-scale structure of the universe. What astronomers call the cosmic web. When you map millions of galaxies across vast regions of space, a pattern emerges. Galaxies aren't distributed randomly. They form long filaments and sheets, like a cosmic spider web, separated by enormous voids where almost nothing exists. This structure is shaped by dark matter, the invisible substance that makes up about 85% of the universe's matter. Dark matter's gravity pulls regular matter together along preferential directions, creating the filamentary structure we observe. In the standard model, this structure forms gradually. Tiny quantum fluctuations in the early universe, imprinted during the inflationary epoch, grow over time under gravity's influence. Small clumps merge into larger clumps. Over billions of years, the cosmic web emerges. Computer simulations of this process are remarkably successful. Start with the initial conditions from the cosmic microwave background, let gravity do its work for 13.8 billion years, and you get something that looks very much like the real universe. But here's the problem: James Webb is finding elements of cosmic structure, filaments, protoclusters, organized galaxy groups, appearing much earlier than simulations predict, at redshifts of 710 corresponding to 500 million years after the Big Bang. Webb has detected what appear to be proto-clusters over densities of galaxies that seem to be in the process of forming galaxy clusters. In the standard model, galaxy clusters are late-forming structures. They require time for many galaxies to collect in a region, drawn together by the gravity of an underlying dark matter halo. The largest galaxy clusters we observe today took billions of years to assemble. Yet Webb is seeing their precursors already forming when the universe was less than 5% of its current age. There's also the question of smoothness. The cosmic microwave background is extraordinarily smooth, temperature variations of only 1 part in 100,000. This smoothness tells us the early universe was very homogeneous, with just tiny ripples that would eventually grow into structure. But growing from such tiny ripples to large galaxies and filaments takes time for gravity to amplify those small differences into significant structures. James Webb's observations suggest the amplification happened faster than it should have. The universe went from nearly perfectly smooth to significantly structured in a shorter time than our models predict. Some researchers have proposed that dark matter might behave differently in the early universe, perhaps being warmer, or more interactive than in the standard cold dark matter model. This could speed up structure formation. But changing the properties of dark matter has ripple effects throughout cosmology. It would affect many other predictions, and it's not clear that these modifications would remain consistent with all our other observations. The Hubble tension, a growing crisis. There's another major problem that James Webb has made worse, not better: the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding. You'd think this would be straightforward to measure, but we actually have two different methods that give two different answers. Method 1: early universe measurement. Using the cosmic microwave background, we can determine the conditions of the early universe with exquisite precision. From those conditions, we can calculate how fast the universe should be expanding today. This method gives a Hubble constant of about 60 kilometers per second. Of the Sun's metallicity is stunning. It suggests that star formation began almost immediately after the Big Bang, perhaps as early as 150 million years, and proceeded at a ferocious rate, rapidly building up heavy elements. But this contradicts what we know about the cosmic dark ages. After the cosmic microwave background was emitted at 380,000 years, the universe entered a period where no stars existed yet. It should have taken significant time for gas to cool and collapse into the first stars. If stars were forming at 100 million years and already producing significant heavy elements by 300 million years, then the dark ages were much shorter and more eventful than we thought. There's also the pattern of elements. Different types of stars produce different ratios of elements. Massive stars produce a lot of oxygen and neon. Medium mass stars contribute nitrogen and carbon. Supernova explosions produce iron. By analyzing the specific pattern of metallicity, astronomers can infer what kind of stars existed. And what they're finding in these early galaxies is complex mixtures that should require diverse, stellar populations, not just one generation of massive stars, but multiple generations of stars with different masses. Again, this requires time the standard cosmology says we don't have. The problem of primordial gas clouds. James Webb isn't just looking at galaxies, it's also observing the space between galaxies, where clouds of primordial gas lurk. These gas clouds, made mostly of hydrogen with traces of helium, are relics from the early universe. Studying them tells us about conditions before and during the epoch of galaxy formation. In the Standard Model, these clouds should be chemically pristine in the earliest epochs, pure hydrogen and helium with no contamination from heavy elements. But Webb is finding metallicity even in these intergalactic gas clouds at high redshifts. This is particularly puzzling because these clouds aren't always associated with galaxies. They're out in the middle of nowhere. So where did the metals come from? The likely answer is that early supernovae were powerful enough to blast enriched material out of galaxies entirely, polluting the surrounding intergalactic medium. This tells us that star formation and stellar death were not only happening early, but happening vigorously enough to significantly alter the chemical composition of intergalactic space. There's also the temperature of these clouds. Some are cooler than expected, suggesting they haven't been heated by the radiation from early stars as much as models predict. Others are hotter, suggesting more energetic processes. Neither pattern quite fits what we'd expect from standard structure formation scenarios. When did the first stars actually form? All of these observations point to a fundamental question. When did the first stars actually form? In the Standard Model, population Earth stars should have formed around 100–200 million years after the Big Bang, perhaps a bit earlier in the densest regions. But if we take James Webb's observations seriously, the early metallicity, the mature galaxies, the massive black holes, it suggests star formation began much earlier, perhaps at 50–100 million years or even before. The problem is that the physics doesn't easily allow this. For stars to form, you need gas to cool and collapse. Cooling requires time and specific conditions. In the very early universe, gas is hot and dispersed. Cooling mechanisms are limited because there are no heavy elements to radiate heat away efficiently. The primary cooling mechanism is molecular hydrogen, but it's fragile and easily destroyed by ultraviolet radiation. Some cosmologists are now proposing that the first stars might have formed in ways we didn't anticipate, perhaps in the dense hearts of dark matter halos, where gravitational effects could overcome the cooling bottleneck. Others suggest that dark matter itself might play a more active role, either by interacting weakly with normal matter or by annihilating and injecting energy into gas clouds, triggering earlier collapse. These are exotic ideas that push beyond the Standard Model, but the observations seem to demand exotic explanations. The redshift puzzle deepens. Underlying all of these problems is the assumption that redshift reliably tells us distance and time. Redshift measurements themselves are solid. We can measure them with high precision. The question is interpretation. Does a Galaxies 12 really exist 370 million years after the Big Bang, or might something else be going on? In the standard cosmological model, redshift is directly tied to the expansion of space. As space expands, light traveling through it gets stretched, increasing its wavelength. The amount of stretching tells us how much the universe has expanded since the light was emitted, which in turn tells us the age of the universe at that time. This interpretation relies on general relativity and the assumption that space expands uniformly according to well-understood physics. But what if space doesn't expand uniformly? What if there are quantum effects, or variations in dark energy, or interactions we don't understand affect light over cosmic distances? An old idea called tired light, proposed in the 1920s but largely abandoned, suggested that light loses energy over long journeys not because of expansion, but through interactions with matter or fields in space. This energy loss would also cause redshift. Tired light was dismissed because it couldn't explain certain observations, like the time dilation seen in distant supernovae, or the precise pattern of the cosmic microwave background. But some researchers are now wondering if a modified version, incorporating aspects of both expansion and energy loss, might better explain what Webb is seeing. If redshift doesn't purely measure expansion, then our cosmic timeline could be significantly different. Those early, massive galaxies might not be quite as early as we think. we might be looking at a universe that's older, or structured differently, than the standard model suggests. This is dangerous territory scientifically, because redshift underpins so much of cosmology. Questioning it is like pulling at a thread that could unravel the entire tapestry. But when observations don't fit the model, something has to give. The return of cyclic cosmologies, when a dominant scientific theory starts showing cracks, old alternatives often resurface. One of the most intriguing is the idea that our universe might not have a singular beginning, that it might be part of an eternal cycle. These are called cyclic or bouncing cosmologies, and they propose that the universe undergoes repeated expansions and contractions. Instead of the Big Bang being the absolute beginning of everything, it's just the latest bounce, the transition from a previous contracting universe to our current expanding one. The basic idea goes like this: a universe expands for billions of years, much like ours is doing now. Eventually the expansion slows and reverses. The universe begins contracting. As it contracts, matter and energy become increasingly dense and hot. In the classical Big Bang, this contraction would end in a singularity, a point of infinite density where physics breaks down. But in modern cyclic models based on quantum gravity, something different happens. Quantum effects create a repulsive force that prevents the singularity. The universe reaches an extremely small but non-zero size, then rebounds into a new expansion phase. This is called the Big Bounce. The beauty of this model is that it illuminates the singularity problem, that awkward point where all our equations blow up and give infinite answers. Instead of a beginning where physics doesn't apply, you have a smooth transition between universes. But more importantly for James Webb's observations, a cyclic universe could naturally explain early structure. If our universe inherited structure from a previous cycle, if the collapse and bounce preserved some information about the configuration of matter and energy from the previous universe, then the early universe might not be starting from scratch. Those massive galaxies Webb sees at high redshift might not be premature. They might be reformations, carrying patterns and structures forward from a previous cosmic era. This idea has serious mathematical backing. Roger Penrose, a Nobel Prize-winning physicist, proposed a model called conformal cyclic cosmology. In his model, the infinite future of one universe becomes the Big Bang of the next. Here's how: as a universe expands forever, eventually all matter decays into massless particles. When everything is massless, there's no way to measure time or distance. The far future of an old universe becomes mathematically identical to the Big Bang of a new one. In Penrose's model, each mine can last trillions of years. But the transition between them is seamless. Information can pass from one aeon to the next, potentially explaining why our early universe looks so mature. It's not actually the first chapter, it's a continuation. Critics point out that cyclic models have their own problems. One major issue is entropy, the measure of disorder. The second law of thermodynamics says entropy always increases. If the universe bounces and restarts, what happens to all that entropy? Does it reset? And if so, how? Some cyclic models suggest each bounce makes the universe slightly larger, diluting entropy across ever more space. Others propose mechanisms for dumping entropy into other dimensions or universes. These solutions are speculative, but they're being taken seriously because the alternative, accepting that galaxies violated the standard timeline, seems equally problematic. Steady-state and quasi-steady-state models, before the Big Bang became dominant, the leading alternative was the steady-state theory, proposed in 1948 by Hermann Bondi, Thomas Gold and Fred Hoyle. Steady-state proposed that the universe has no beginning or end. Yes, it's expanding, Hubble's observations made that clear, but as it expands, new matter is continuously created from the vacuum to maintain a constant density. The universe looks roughly the same at all times and places. This was philosophically appealing. It avoided the awkward question of what came before the beginning and eliminated the need for special initial conditions. The theory was largely abandoned in the 1960s after the discovery of the cosmic microwave background, which steady state couldn't easily explain. If the universe is eternal and unchanging on average, where did this pervasive background radiation come from? But Fred Hoyle never fully gave up. In the 1990s, along with colleagues Geoffrey Burbidge and Jayant Narlikar, he proposed a modified version called quasi-steady-state cosmology. QSSC keeps the eternal universe concept but adds periodic, mini-bangs, localized creation events scattered throughout space and time. These mini Bangs could explain the CMB as the combined afterglow of many creation events, not just one. In the age of James Webb, QSSC is getting a second look. If the universe is far older than 13.8 billion years, if it's actually eternal, then there's no puzzle about how structure formed so quickly. It didn't form quickly. It had unlimited time. Those early, massive galaxies. They're not early at all. They're just distant, and our interpretation of their age based on redshift might be wrong. QSSC isn't widely accepted, it struggles to match some observations, particularly the precise pattern of the cosmic microwave background. But it represents a way of thinking that's becoming less taboo. Maybe the universe doesn't have an age. Maybe it's always existed. Plasma cosmology, the electromagnetic universe. On the more controversial fringes sits plasma cosmology, a framework developed largely by Nobel Prize-winning physicist Hans Alfvén. Plasma cosmology argues that cosmologists have been too focused on gravity while ignoring electromagnetism, even though plasma makes up 99% of the visible universe. In this model, the large-scale structure of the universe is shaped not primarily by gravity and dark matter, but by vast electric currents and magnetic fields threading through space. These electromagnetic forces can be far stronger than gravity over certain scales, and can organize matter into filaments and structures more efficiently. Plasma cosmology doesn't accept the Big Bang. Instead, it proposes an eternal universe structured by electromagnetic interactions. Redshift, in this view, isn't caused by expansion but by light losing energy through interaction with the pervasive plasma medium, a version of tired light. The theory has been heavily criticized for failing to explain key observations like the cosmic microwave background's pattern and the abundance of light elements. Most mainstream cosmologists dismiss it. But plasma cosmology did predict some aspects of cosmic structure, particularly the filamentary nature of galaxy distributions, before they were observed. And it offers natural explanations for rapid structure formation, since electromagnetic forces can act much faster than gravity alone. With James Webb challenging conventional timelines, a few researchers are asking, did we dismiss plasma effects too hastily? Could electromagnetic forces play a larger role in the early universe than the standard model accounts for? This doesn't mean plasma cosmology is correct, but it suggests we might need to incorporate more plasma physics into our models. Emergent spacetime and quantum foundations. Perhaps the most radical alternative doesn't question when the universe began, but whether space and time are real at all. A growing number of physicists are exploring the idea that spacetime is emergent, not a fundamental aspect of reality, but something that arises from deeper quantum processes, like temperature emerging from molecular motion. In this view, space and time are not the stage on which physics happens. They're phenomena that appear when you look at quantum information at large scales. The mathematics comes from several cutting-edge fields, quantum entanglement and EPRA. A proposal by physicists suggests that quantum entanglement, the spooky action at a distance that bothered Einstein, might actually create spacetime connections. Two entangled particles aren't connected through space, they might be connected by space, with entanglement literally budding the geometry. Holographic principle. Based on black hole physics, the holographic principle suggests that all the information in a volume of space can be encoded on the boundary of that volume. The universe might be like a hologram, where the three-dimensional reality we perceive emerges from information stored on a two-dimensional surface. Loop quantum gravity. This approach tries to quantize space itself, suggesting that space is not continuous but made of discrete units, quantum grains, of space linked together in a network. In this framework, spacetime is an emergent property of the network, and concepts like distance and time arise from the relationships between these quantum nodes. If spacetime is emergent, what does that mean for the Big Bang? It could mean the beginning. Isn't a moment in time at all, but rather the point where our emergent description of spacetime becomes useful. Before that, there's no meaningful before, because time itself hasn't emerged yet. For James Webb's observations, this offers a potential way out if spacetime behaves differently, in what we call the early universe, if the relationship between redshift, distance, and time isn't constant, then galaxies might not be as temporally young as they appear. They might exist in a regime where our usual spacetime concepts break down, where structure can exist without having formed in the way we understand formation. This is deeply speculative, but it's grounded in real theoretical physics. Researchers at institutes studying quantum gravity are taking these ideas seriously. The modified gravity approach, another avenue being explored. What if gravity itself works differently at cosmic scales? Einstein's general relativity has passed every test we've thrown at least in our local cosmic neighborhood. But what if the rules change when you're dealing with the entire universe? Modified Newtonian dynamics, proposed by physicist Mordechai Milgrom, suggests that gravity behaves differently when accelerations are extremely small, the kind of accelerations you see in galaxy rotation or cosmic expansion. MAMD was originally proposed to explain galaxy rotation curves without invoking dark matter, and it does this successfully for many galaxies. But it struggles to explain larger structures like galaxy clusters and the cosmic microwave background. Recently, some researchers have proposed combining MODI-like modifications with some dark matter, or incorporating OND effects into a full relativistic theory of gravity. If gravity is modified at cosmic scales, it could affect structure formation timelines. Galaxies might assemble faster than general relativity predicts, potentially explaining Webb's observations without requiring radical changes to the Big Bang framework. TAVIS and other modified gravity theories are being tested against new observations. James Webb's data will be crucial in determining whether these alternatives can match observations better than the standard model. The multiverse possibility. Here's a different kind of explanation: maybe our universe is just weird. If the multiverse hypothesis is correct, if there are countless universes with different properties, then our universe might just happen to have unusual initial conditions that allowed structure to form faster than typical. In the multiverse framework, different universes might have different values for fundamental constants, different amounts of dark matter and dark energy, different inflation parameters. Most universes might be boring, either collapsing immediately, or expanding too fast for structures to form, or having constants that don't allow complex chemistry. We find ourselves in a universe that permits life because, well, we couldn't exist in the others. This is the anthropic principle. If we're in an atypical universe, one of the rare ones where early structure formation was possible, then James Webb's observations might not contradict the Big Bang so much as show us that we're in a special case. The problem with this explanation is that it's not really testable. If every observation can be explained by saying, "We're in an unusual universe," then we've given up on finding universal laws. Still, if the standard model truly can't account for what we're seeing, the multiverse might be a fallback explanation, one that's philosophically unsatisfying, but logically possible. The scientific debate defenders vs revolutionaries. The scientific community is grappling with all of this in real time, and the debate is intense. On one side are the defenders of the standard model. They argue that CDM has earned its place through decades of successful predictions. Yes, Webb has found surprises, but surprises aren't fatal. They're opportunities to refine the model. These researchers point out that our understanding of early star formation is still incomplete. Maybe population through stars were more diverse than we thought. Maybe they form more efficiently. Maybe we're underestimating how quickly galaxies can assemble through mergers in high-density regions. They also note that observational challenges remain. Measuring the properties of extremely distant galaxies is difficult. Dust can mimic certain spectral features. Gravitational lensing can magnify and distort images. Maybe some of Webb's most extreme observations will be revised as we better understand the systematics. Let's not throw out a century of successful physics because of a few years of new data. One prominent cosmologist argues. Let's be patient and see where the observations lead. On the other side are researchers calling for more radical rethinking. They see Webb's observations not as minor puzzles, but as fundamental challenges that the standard model cannot accommodate without tortured modifications. At some point, you have to ask whether you're saving the model or just patching it endlessly. Another researcher counters. History shows that when observations consistently contradict theory, it's usually the theory that's wrong, not reality. This camp is more willing to explore alternatives, cyclic models, modified gravity, emergent spacetime, even revisiting tired light. They argue that scientific progress requires willingness to challenge foundational assumptions. The middle ground is occupied by researchers who see value in both approaches. They're running sophisticated simulations that incorporate more realistic physics, magnetic fields, plasma effects, better modeling of feedback from stars and black holes, to see if refined versions of the standard model can match observations. They're also designing new observations to test specific predictions. If the standard model is right, what should we see next? If alternatives are right, what would distinguish them? What observations would settle it? So what would actually resolve this? What observations could tell us whether the Big Bang needs modification, replacement, or just refinement? 1. Population theory. Stars. Finding a genuine zero metallicity star would confirm that the early universe had a pure hydrogen-helium phase. Conversely, if we keep finding metallicity everywhere we look, it suggests either stars formed much earlier than thought, or there's a different source of heavy elements. 2. The 21 cm line. Before stars formed, the universe was filled with neutral hydrogen. This hydrogen should emit radiation at a specific wavelength, 21 centimeters. Detecting this signal from the cosmic dark ages would tell us when the first stars actually ignited, and how they affected their surroundings. Several experiments are attempting this challenging observation. 3 gravitational waves. Space-based gravitational wave detectors like LESAIR might detect waves from the early universe, potentially from colliding black holes, from cosmic inflation, or even from phase transitions in a bouncing universe. These waves would carry information about conditions we can't access with light. 4. More distant galaxies. James Webb will continue pushing to higher redshifts. If we keep finding mature galaxies at redshift 15, 17, 20, that increasingly strains the standard model. At some point, we should see galaxies transitioning to simpler structures. If we don't, that's a problem. 5. Better CMB measurements. Next generation CMB experiments might detect subtle patterns that distinguish between standard inflation, cyclic models, or other alternatives. The polarization of the CMB, how the light waves are oriented, contains clues about what happened in the first moments. 6. Direct dark matter detection. If dark matter particles are finally detected in Earth-based experiments, that would strengthen confidence in DCDM. If they continue to evade detection, it might suggest dark matter isn't a particle at all, potentially opening the door to modified gravity or other alternatives. The next decade will be crucial. We're entering an era of unprecedented observational power, with multiple new telescopes and experiments coming online. The philosophical implications, a universe without beginning. Let's step back from the technical details, and think about what all of this means, not just for physics, but for our place in the cosmos, and how we understand existence itself. Humans have always asked, where did everything come from? Every culture has creation myths. The ancient Greeks had chaos giving birth to order. Norse mythology has ice and fire meeting to create the world. Many religions have a creator bringing the universe into being with intention and purpose. The Big Bang Theory, in a way, was science's creation story. It gave us a specific beginning. 13 billion years ago, everything emerged from an incredibly hot, dense state. Time began, space began. The universe had a birthday. This was philosophically satisfying in many ways. It provided a definite answer to when. It established a timeline, an arrow of time pointing from simple to complex. It gave existence a starting gun. But it also raised uncomfortable questions. What came before? What caused the Big Bang? Why did it happen? Why those particular initial conditions and not others? The standard response was that these questions might be meaningless. If time itself began with the Big Bang, there is no before. Asking what came before time is like asking what's north of the North Pole. The question doesn't make sense within the framework. But now, James Webb might be showing us that this framework is incomplete or wrong. If the universe is cyclic, if our Big Bang was actually a big bounce from a previous universe, then there's no ultimate beginning. It's turtles all the way down, or rather, bounces all the way back. If the universe is eternal and steady state, or if time is emergent rather than fundamental, then again there's no beginning. The universe didn't come from anything. It simply is. What does this do to our sense of meaning and purpose? For some, it might feel liberating. An eternal universe has no need for a first cause, no need for something outside itself to bring it into being. Existence just is, no explanation required, no creator needed. We're not part of a story with a beginning, middle, and end. We're just moments in an endless process. For others, this might feel unsettling or even meaningless. If the universe has no beginning, no direction, no destination, then what gives our lives significance? Are we just random fluctuations in an eternal cosmic machine? But maybe that's the wrong question. Maybe meaning isn't something the universe gives us, it's something we create. In a universe with a definite beginning and presumed end, you might feel like you're following a script. But in an eternal beginningless universe, there's no script. Every moment is equally valid. Every experience equally real. The meaning of your life isn't determined by where the universe came from. It's determined by what you do with your brief, precious moment of awareness. This is existential philosophy meeting cosmology. And it matters because how we understand the universe shapes how we understand ourselves. Science at the edgy. Living through a paradigm shift, we might be living through one of moments in history when a scientific paradigm shifts. The philosopher Thomas Kuhn described how science evolves. Most of the time scientists work within an established framework, what Kuhn called normal science. They solve puzzles, refine measurements, fill in details. The big picture is settled, the work is about getting the specifics right. But occasionally, anomalies accumulate, observations that don't quite fit, puzzles that resist solution. At first, these are dismissed or explained away. But eventually, they pile up to the point where the framework itself comes into question. That's when paradigm shifts happen. Not smoothly, not easily, but through a period of crisis and debate. Old guard scientists defend the established view. Young mavericks propose alternatives. Data is scrutinized, reanalyzed, debated. Eventually, either the anomalies are resolved within the existing framework, or a new framework emerges that better explains the full range of observations. We've seen this before in physics. When observations of planetary motion led to heliocentrism replacing geocentrism, when the photoelectric effect and black body radiation led to quantum mechanics, when Mercury's orbital precession and other observations led to general relativity replacing Newtonian gravity. Each time, the old framework wasn't completely wrong, it was incomplete. Newtonian gravity still works perfectly well for everyday situations. It's just not the full picture. James Webb might be pushing us toward another such moment. The Big Bang framework has been extraordinarily successful. It explains cosmic expansion, the cosmic microwave background element abundances, and large-scale structure. These successes won't disappear. But if the framework can't accommodate early galaxy formation, rapid structure formation, and the other anomalies Webb is revealing, then something has to give. Either we'll modify the framework, adding new physics, refining parameters, incorporating effects we've neglected, or we'll eventually develop a new framework that encompasses the old one as a special case. The exciting thing is we get to watch this happen in real time. What makes this different? The speed of modern science. Previous paradigm shifts played out over decades or even centuries. When Copernicus proposed heliocentrism in 1543, it took over 100 years for the idea to be widely accepted. When Einstein proposed relativity in 1905, it took decades for the experimental confirmations to accumulate and for the theory to become mainstream. But we live in a different era now. James Webb launched in December 2021. Within a year, it was delivering data that challenged century-old ideas. Within 2 years, cosmologists worldwide were grappling with the implications, publishing papers, running new simulations, proposing alternatives. The scientific conversation is happening at unprecedented speed, accelerated by instant global communication. Researchers across continents collaborate in real time, sharing data and ideas immediately. Computational power simulations that would have taken years now run in weeks or days, allowing rapid testing of new hypotheses. Public engagement. The internet allows the public to follow along, reading preprints, watching lectures, engaging with the science as it unfolds. This democratization and acceleration of science is remarkable. But it also creates challenges. In the past, paradigm shifts happened largely behind closed doors, in journals, at conferences, in private correspondence between researchers. The public learned about the revolution only after it was mostly settled. Now, the public is watching the messy middle part, the uncertainty, the debates, the contradictions. This can create confusion. One headline says, Big Bang confirmed, another says, Big Bang under fire. Which is it? The answer is both kind of. Science is a process, not a product. What we're seeing is science doing what it does, questioning, testing, adapting. The confusion is part of the process. The role of future missions. James Webb is revolutionary, but it's not alone. The next decade will see a fleet of new observatories that will help resolve these questions. Nancy Grace Roman Space Telescope. Roman will have a field of view 100 times larger than Hubble's. While Webb excels at deep, detailed looks at small regions, Roman will map vast areas of sky. This will tell us whether Webb's anomalies are everywhere or just in specific unusual regions. Vera C. Rubin Observatory. Rubin will conduct a 10-year survey called the Legacy Survey of Space and Time, cataloging billions of galaxies and tracking how they change. This time, domain astronomy will show us the universe in motion, revealing dynamics we can't see in single snapshots. Extremely large telescope with a 39-meter primary mirror, nearly 6 times the diameter of Webb's mirror, the ELT will be the largest optical telescope ever built. Operating from the ground, it can be upgraded and maintained, giving it longevity that space telescopes lack. LISA will detect gravitational waves from space, opening an entirely new way to study the universe. Gravitational waves from the early universe could carry information about cosmic inflation phase transitions, or even colliding universes in a cyclic model, CMB, S4Z. Building on Planck's legacy, CMB S4 will map the polarization of the cosmic microwave background with unprecedented precision, potentially detecting signatures of inflation or other early universe phenomena. Together, these missions form a comprehensive approach: wide surveys, deep looks, multiple wavelengths, gravitational waves, particle detection. Each puzzle piece will help complete the picture. The dark matter question. Running through all of this is a deeper mystery: dark matter. Dark matter is supposed to be the scaffolding of the universe, the invisible mass whose gravity pulls regular matter together, enabling galaxies and larger structures to form. We've never directly detected dark matter particles. We infer their existence from gravitational effects, galaxy rotation curves, gravitational lensing, the cosmic microwave background pattern. The standard model assumes dark matter is cold, meaning the particles move slowly, and that it interacts only through gravity, not through electromagnetic or other forces. But what if dark matter is more complex than we thought? Some researchers propose that dark matter might be warm, or self-interacting, properties that would affect how quickly structure forms. Others wonder if dark matter exists at all, suggesting instead that we need modified laws of gravity. James Webb's observations could help discriminate between these options. If we can figure out exactly how structure formed in the early universe, we can work backward to determine what dark matter must be like, or whether it exists. One intriguing possibility: dark matter might have played an active role in seeding early galaxies. Perhaps dark matter halos collapsed first, creating gravitational wells into which normal matter fell, forming stars and galaxies around these invisible anchors. If so, understanding dark matter isn't just about exotic particle physics. It's fundamental to understanding how galaxies, including our own, came to exist. The measurement problem: can we trust what we see? There's a philosophical issue lurking beneath all of this. How do we know our measurements are correct? When James Webb looks at a galaxy at redshift 12 and measures its mass, how confident can we be in that measurement? Galaxy mass is typically estimated by measuring light output and applying models of stellar populations, how much light stars of different masses produce. But these models are calibrated on nearby, modern galaxies. Do they apply to early galaxies that formed under very different conditions? Similarly, measuring distances relies on understanding redshift, and redshift interpretation relies on assuming we understand cosmic expansion. If the expansion history is different from what we think, then our distance, and therefore age, estimates could be systematically wrong. This isn't to say measurements are meaningless. There are best estimates given current understanding. But there's an inherent circularity. We use models to interpret observations, then use those observations to validate models. Breaking this circularity requires independent checks, multiple methods of measuring the same thing, looking for consistency across different types of observations. That's partly why the Hubble tension is so troubling. We have two independent ways to measure the universe's expansion rate, and they disagree. That tells us something is systematically wrong with at least one method, or possibly both. As we push to the limits of observational capability, these systematic uncertainties become more important. We're not just measuring what's out there, we're testing whether our measurement tools themselves are reliable. What hasn't changed? The successes of the Big Bang. It's important to emphasize it. Despite the challenges, the Big Bang framework hasn't failed. The cosmic microwave background is still there, matching predictions made decades before its discovery. The abundances of light elements still match Big Bang nucleosynthesis calculations. The expansion of space is still directly observed. These aren't small achievements. They're foundational confirmations that any alternative theory must also explain. What's being challenged isn't whether the universe expanded from a hot, dense state. It's the details, exactly when structure started forming, how quickly it happened, whether the timeline we've constructed is accurate. This is like the transition from Newtonian gravity to general relativity. Newton's laws didn't stop working, they're still perfectly adequate for most situations. But Einstein showed they were a special case of a more complete theory. Similarly, the Big Bang might be a special case or an approximation of something deeper. The expansion, the cooling, the formation of elements, these might all be correct as far as they go, but incomplete. The question is, what's the more complete picture? The human element. Why scientists resist change? It's worth acknowledging the human side of this debate. Scientists aren't dispassionate robots analyzing data without bias. They're people who've devoted their lives to certain ideas, built their careers on specific frameworks, and have emotional as well as intellectual investments in their work. Many cosmologists have spent decades working within the key CDM framework. They've written textbooks, taught students, built entire research programs around it. Accepting that it might be fundamentally wrong is psychologically difficult. This doesn't mean scientists are closed-minded. The best ones are keenly aware of their biases and work hard to remain objective. But it does mean that paradigm shifts face institutional and psychological resistance, not just intellectual challenges. Younger researchers, who haven't invested as much in the existing paradigm, are often more open to alternatives. They have less to lose and more to gain from revolutionary ideas. This generational dynamic is part of how science progresses. As physicist Max Planck famously observed, a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. That's perhaps too harsh. Many scientists do change their minds when confronted with compelling evidence. But it captures a real phenomenon. Scientific change is not just about data, it's about people. Why this matters to everyone, you might be wondering. Why should anyone who's not a professional cosmologist care about this? Here's why. These questions touch on fundamental aspects of human existence. Origin, where do we come from? Does the universe have a beginning, or is it eternal? These aren't just academic questions, they shape how we understand ourselves and our place in existence. Meaning, is the universe following some trajectory from a beginning toward an end, or is it an endless cycle with no ultimate purpose? This affects how we think about meaning, significance, and whether there's any cosmic story we're part of. Humility, being confronted with how much we don't know. Realizing that our best theories might be wrong, is a profound lesson in humility. The universe doesn't owe us answers we can understand. Reality is what it is, regardless of our theories. Wonder, there's something deeply exciting about living in a time when major questions are unsettled. We get to witness scientific revolutions, see human knowledge expanding in real time, and participate in the eternal human quest to understand the cosmos. These questions also have practical implications. The technologies that enable James Webb, advanced optics, cryogenics, spacecraft engineering, data processing, all have applications beyond astronomy. The computational methods developed to analyze cosmic data get used in medicine, climate science, artificial intelligence. And perhaps most importantly, wrestling with these questions exercises our capacity for rational thought, evidence-based reasoning, and intellectual honesty, skills that matter far beyond cosmology. The current state, where do we stand? As of early 2025, here's where things stand. The James Webb Space Telescope continues operating beautifully, returning data that grows richer and more puzzling with each observing cycle. The initial surprises haven't gone away. They've been confirmed and extended. The cosmology community is deeply engaged in trying to understand the observations. Dozens of research groups are running simulations, analyzing data, proposing modifications to the standard model, and publishing papers at a rapid pace. There's no consensus yet on how to resolve the tensions. Some researchers think we just need better models of early star formation. Others think we need new physics, perhaps related to dark matter, dark energy, or inflation. A smaller but growing group thinks we need more radical changes. What's clear is that this isn't going away. The anomalies are real, the observations are solid, and the timeline problem is genuine. The next few years will be crucial. As more data accumulates, patterns will become clearer. Some proposed explanations will be ruled out. Others will gain support. We might be on the verge of a genuine paradigm shift, or we might find that the standard model, with some modifications, can accommodate everything we're seeing. Either way, we're living through an extraordinary moment in the history of science. What you can do, if you find this fascinating, and if you've stuck with me this long, you probably do, here's what you can do: stay informed, follow space agencies like NASA and ESA. Read science news from reputable sources. Watch for announcements about new James Webb discoveries. Think critically when you see headlines like, Big Bang disproven. Look deeper. Read the actual research if you can. Understand that science is messy and that headlines often oversimplify. Embrace uncertainty, get comfortable with, we don't know. It's okay that the universe is puzzling. That's what makes it interesting. Share the wonder, talk about these ideas with friends, family, kids. Science isn't just for scientists, it's humanity's shared project of understanding reality. Support science, whether through advocacy for research funding, supporting science education, or just valuing evidence-based thinking in your own life. You can contribute to the scientific enterprise. The beauty of not knowing, there's something profound about living in a time when we don't have all the answers. For a while it seemed like cosmology was mostly figured out. The Big Bang happened. The universe expanded, galaxies formed over time, and we understood the basic story. There were details to fill in, but the outline was clear. James Webb has reminded us that the universe is stranger and more wonderful than we imagined. It's given us new mysteries to solve, new questions to ask, new horizons to explore. Not knowing is uncomfortable. Humans crave certainty. We want solid ground beneath our feet. But not knowing is also exhilarating. It means there's more to discover. It means the story isn't over. It means each new observation could reveal something unprecedented. The universe doesn't care what we think should be true. It is what it is. Our job is to look honestly, think carefully, and follow the evidence wherever it leads, even if it leads us to conclusions that challenge everything we thought we knew. That's the essence of science. Not claiming to have final answers, but being willing to question, to test, to revise our understanding when reality demands it. The long view, what history will remember. Decades from now, when we look back at this period, what will we remember? Maybe we'll remember it as the time when the Big Bang theory was refined and strengthened. When observations that initially seemed challenging were ultimately incorporated into an expanded framework. Or maybe we'll remember it as the beginning of a revolution. When James Webb first revealed that our understanding of the universe was incomplete, sparking a transformation in cosmology that took decades to fully unfold. Either way, we'll remember that a telescope, a marvel of human ingenuity, launched a million miles from Earth, opened our eyes to aspects of the cosmos we'd never seen before. We'll remember the scientists who built it, the researchers who analyzed its data, and the communities who grappled with its implications. And we'll remember that humans, tiny creatures on a small planet orbiting an ordinary star, dared to ask the biggest questions imaginable, and built tools sophisticated enough to begin answering them. That alone is remarkable. Whatever the ultimate answers turn out to be, the fact that we're asking these questions, that we're capable of building something like James Webb, that we're willing to challenge our most fundamental assumptions, that's a triumph of human curiosity and intellect. So, night owls, where does that leave us? We've journeyed from the James Webb Space Telescope's stunning images to the deepest questions about existence itself. We've seen how galaxies that shouldn't exist are forcing us to reconsider everything. We've explored alternative cosmologies, from cyclic universes to emergent spacetime. We've grappled with what it means if the universe has no beginning. The honest answer to, what's really going on, is we don't know yet. The James Webb Space Telescope has given us extraordinary new data. That data challenges the standard model of cosmology in ways we can't easily dismiss. But science doesn't move on sensationalism, it moves on accumulated evidence, rigorous testing, and careful reasoning. Over the next decade, we'll see how this unfolds. More observations will either strengthen the case for a paradigm shift, or reveal that the standard model, perhaps with modifications, can accommodate what we're seeing. What we know for certain is this: the universe is more mysterious, more complex, and more wonderful than we thought. And that's beautiful. It means we're not done discovering. It means the next generation of scientists will have big questions to tackle. It means the story of how we came to be, how the universe evolved from whatever beginning or beginningless state it had into the rich, structured cosmos we observe, is still being written. For those of us watching from the sidelines, it's a privilege to witness. We're living through a golden age of cosmology, when our instruments are powerful enough to probe the edge of existence and our theories are being tested in ways they never have been before. Maybe the Big Bang happened exactly as we thought, and we just misunderstood some details about early galaxy formation. Maybe the Big Bang is part of a larger cyclic process, one bounce in an eternal series. Maybe time and space themselves are emergent phenomena, and our entire framework of cosmology needs reimagining. Whatever the truth turns out to be, the universe is under no obligation to make sense to us. It is what it is. Our models are just models, useful tools for organizing our observations and making predictions, but not reality itself. The map is not the territory. And sometimes the territory surprises us, so stay curious, friends, keep asking questions. Keep looking up. And remember that not knowing all the answers is not a weakness. It's the starting point of every great discovery. If you enjoyed this deep dive into one of science's biggest current mysteries, do me a favor, hit that like button to help this reach other curious minds. Subscribe to Late Night Science for more explorations into the questions that keep scientists, and hopefully you, awake at night. And drop a comment. Tell me, what do you think? Is the Big Bang on borrowed time? Are we witnessing a scientific revolution? Or will these anomalies ultimately be explained within the existing framework? I genuinely want to know what you think. Check the description for links to paper articles and resources if you want to dig deeper. And if you want to support the channel, consider becoming a member. It helps me keep making these long-form explorations of cutting-edge science. Until next time, keep wondering, keep questioning, and keep looking for answers in the darkness. This is Late Night Science. Thanks for staying up with me. Good night and clear skies.